Okay, we're just going to look at some of these formulas that you need to know for the higher level content on oscillators. The first two formulas are probably the most difficult one, and we'll spend a bit more time doing those. The others are fairly straightforward and self-explanatory. So you remember that when we did the simple harmonic motion, the displacement graph, which is the one at the top, is basically a sine function of t. In fact, it's omega t, which is 2 pi f times pi t. So the sine of 2 pi f t. We're going to look at the velocity formula later. So the first one is x, which is the displacement, is the amplitude, which is x naught, times by the sine of omega t. In other words, 2 pi f. Now we're going to use the same formula, and we're going to plug it into Desmos to see what that looks like. So on the left, you see that I have f of t, the function of t, is equal to sine of 2 pi t. Now it should be 2 pi ft, but let's say we'll make the maths a little bit easy and we'll have f is equal to 1. So the frequency is equal to 1, so the time period is equal to 1 over 1, which is 1. So in other words, the time period is 1 second, and we do 1 oscillation per second. Now you see on this graph, the time period, the time taken to go from the middle of the wave up, down, and back to the middle of the wave is 1 second. In that time, it goes through 2 pi radians of angle, mathematically speaking. So the question is, we use the simplest form. Notice that time starts at 0, displacement. So this is if a pendulum were to start in the equilibrium position and start moving from there. So this is a very kind of theoretical, simple expression of this formula. Now, in the data booklet, it's more like this. So in reality, when you have an oscillation system like a pendulum, it doesn't start at equilibrium. They don't start at 0. They start with a non-zero displacement, or in other words, a phase shift. So when you start a pendulum, you pull it to the side first and then release it. So, and that is taken into account by this thing, which is the angular shift or the phase shift, which is this phi, which is put at the end. So now it's not just the sine of omega t, it's the sine of phi. Of course, in this case, phi is equal to 0 because there's no phase shift. However, we're going to start exploring and experimenting with different phase shifts. Let's say, taking the formula on the left, that it's 2 pi t plus 0.2. What does that look like? Well, I did this, and you notice it's the red graph which is slightly shifted to the left by 0.2 radians. So this is, we apply a phase shift of 0.2 radians. And we do another one. This time is 0.5 radians. You see it shifts further to the left. But an important one would be when we get a quarter of an oscillation. Now we know 2 pi radians is a full cycle, and a quarter of that is going to be pi divided by 2. So that's the next one we try. So this is basically how an oscillator will be. You notice that when t is equal to 0, the displacement is at a maximum. And that is the case when you release a pendulum. You move it to the maximum displacement and you release it from there. So the blue graph here would be if it were cosine 2 pi t, and that would be it, starting from the equilibrium position. But in reality, the function is shifted by pi over 2 radians. So the red one is a truer picture of it. So it's going to be 2 pi t or 2 pi ft plus pi divided by 2. Now you have to look at the context of the question, whether you add pi divided by 2 or subtract pi divided by 2. But in the case of a pendulum, when you move it to the side first and you start from that point, then that's going to be exactly the red one here. So it's going to be plus pi divided by 2. The different questions might not have this amount of displacement. It might start at time is equal to 0.1 radian or something like that. But then you have to plug those values in to the formula as appropriate. Yeah, so this is a displacement as if the time starts at a maximum displacement, which is true, which is how you actually operate a pendulum. You move it first. So if we look at a velocity graph, this is a formula for the velocity graph. And here again, it's not just cosine omega t, it's omega t plus the phase shift. So in this case, we're going from the blue one, which is with 0 phase shift. Of course, the pendulum doesn't start with maximum velocity. It starts with the minimum velocity when it's extended to the full maximum displacement, and then it's left to oscillate. So really, the red graph is a much truer picture of what's going on with a pendulum. So you could be asked to use this formula, or the displacement formula. To just quickly review that, x is the displacement, x naught is the amplitude, the omega t is the time-dependent angle, and phi is the phase shift, which is often 0, but sometimes not. But sometimes it's pi over 2 radians or negative pi over 2 radians, depending on the context of the question. But it also could be another value. These are the formulas that go with this topic, and let's just quickly go through each one. This one we've addressed already: displacement, amplitude, the time-dependent angle, and the phase shift. And it's the same for the cosine. For the velocity, gives the cosine. Now this one is v is equal to plus or minus omega x naught squared minus x squared. So x is the displacement and x naught is the amplitude. This is another way of expressing the velocity. And these last two questions about the total energy and the potential energy. So that's total energy of the oscillator, which depends on the mass of the oscillator. It depends on the angular speed, omega. It depends on the amplitude as well. That gives the total energy. The potential energy depends on the same things, except instead of the maximum displacement, it's the displacement at the time. So obviously, if the displacement is 0, the potential energy will be 0. Now, you need to know a little bit about how circular motion and how it can be expressed mathematically as a combination of sine and cosine lines. So now you must have done this in maths already. We've got this circular motion. From the side view, if we start at the 0 point, which is there, we have it's a sine graph. If you view it from 90 degrees from that, it's going to be a cosine graph. So circular motion can be represented as sine and cosine functions. Likewise, simple harmonic motion, since we know it can be expressed as a sine function, it can also be a projection of circular motion onto a linear graph and onto a linear diagram. So you take the circular motion, which is the middle object here, and if you were to view it from the side, from the left side, you would see what it effectively would look like simple harmonic motion. So circular motion and simple harmonic motions are basically, one is like a presentation of the other, a representation of the other.